Hello students, welcome to EPG Pathshala. I am Dr. Devrat Mishra from Department of Physics and Astrophysics, University of Delhi. Today we are going to discuss about the module Dielectric Properties 9 from paper Electronic, Magnetic and Optical Properties of Materials. So students, let us see what we are going to learn in this module. So we will first see the detailed study of ferroelectricity and the dipole theory of ferroelectricity. Secondly, we will see the classification of ferroelectric materials in tartrate, dihydrogen phosphates and arsenates of alkali metals and oxygen octahedron group. Ferroelectricity. Below a certain temperature, it is found that some materials spontaneously acquire an electric dipole moment. By analogy with the magnetic case, these materials are called ferroelectrics. Just as with ferromagnets, these crystals exhibit a hysteresis called P versus E, and this can be explained by a domain hypothesis. These domains are quite easy to observe with polarized light in some materials. The transition to the ferroelectric state is a cooperative phenomenon which is accompanied by specific heat anomaly or by a latent heat, and it appears that at the transition temperature the crystal lattice spontaneously distorts to a more complicated structure which possesses a permanent electric dipole moment. There are three types of crystal structure which exhibit ferroelectricity. One, Rochelle-Salt structure, typically by Rochelle-Salt NaK C4H4O6 with 4H2O. Second, the perovskite group consisting mainly of titanates and neobates, of which barium titanate BaTiO3 has been most extensively studied one, and the dihydrogen phosphates and arsenates, for example KH2PO4, KDP. In ferroelectric materials, the electric flux density D is not determined uniquely by the applied field but depends upon the previous history of the material. Just as ferromagnetics have regions with aligned magnetic moments, so also in ferromagnetics there are large regions which are characterized by the alignment of the electric field. For this region, the electric field turns the whole of such regions in the direction of the field and overcomes the thermal agitation that tends to scatter the electric dipoles in the different directions. The aligned electric fields of such regions of a ferroelectric combiner with the external electric field increasing the flux density thousands of times. The charge of a condenser is increased the same number of times when a ferroelectric is used instead of air. The lower the temperature and the stronger the electric field, the more predominant is the effect of the latter over the random thermal agitation. In sufficiently strong fields, the electric dipoles of all regions of the ferroelectric are practically in the direction of the field. This produces the greatest possible charge density. Condensers made of barium titanate and other ferroelectric materials concentrate considerable quantity of electric charge within a small space as ferrites concentrate magnetic energy. When an electric field is applied to a specimen of a ferroelectric crystal, the polarization first rises rapidly with applied field to a value above which the dependence is linear. Linear extrapolation to zero field gives PS, the saturation or spontaneous polarization. On subsequently reducing the field to zero, residual polarization PR remains. The field to reduce the polarization to zero is called coercive field and is represented by EC. The existence of a dielectric hysteresis loop in a dielectric material implies that the substance possesses a spontaneous polarization and the value of PS depends upon a number of factors such as the dimensions of the specimen, the temperature, the texture of the crystal, and the thermal and electrical properties of the crystal. The hysteresis loop of a ferroelectric material changes its shape as the temperature is increased. The height and width decreases with increase of temperature. At a certain temperature, known as ferroelectric Curie temperature, the loop merges into a straight line and the ferroelectric behavior of the material disappears. Table 1 shows the properties of some ferroelectric materials at room temperature. So here we have a list of crystals, for example, Rochelle salt, BaTiO3, where the Curie temperature is 391, but for Kd2PO4 it is, or potassium niobate KnBO3, the Curie temperature is around 708 Kelvin, and the spontaneous polarization PS in coulomb per meter square is also shown here, which is highest, which is of the order of 10 to the power minus 2 and is around 26 for BaTiO3 and which is less in Rochelle salt. Spontaneous polarization in a ferroelectric material disappears above the Curie temperature. If the temperature is below the Curie temperature, the polarization or dielectric constant is not a linear function of the field and epsilon r is not a constant, and so the equation P equals to E epsilon 0 into epsilon r minus 1 cannot be applied directly. In such cases, epsilon r for a ferroelectric material may be defined for the virgin curve as a differential quantity. So dP by dE is equal to epsilon 0 into epsilon r minus 1. We know that the internal field EI is equal to E plus beta P by epsilon 0 and P is equal to N into alpha EI, which is equal to alpha E plus alpha I plus alpha 0, that is P equals to N into alpha into E plus beta P by epsilon 0. Figure 1 shows the hysteresis loop of a ferroelectric material, and B1b represents PE relation above Curie temperatures. So from that we get P into 1 minus N alpha beta by epsilon 0 is equal to N into alpha into E, or P equals to N alpha E divided by 1 minus N alpha beta by epsilon 0. If 1 minus N alpha beta by epsilon 0 is equal to 0, one gets a non-vanishing solution for P, and therefore there exists the possibility of spontaneous polarization. We may conclude now that with 1 minus N alpha beta by epsilon 0 equals to 1, the dielectric constant will become infinite and the substance will become spontaneously polarized. Beta is equal to 1 by 3 for cubic structure. Dipole theory of ferroelectricity. The interaction between adjacent dipoles in a ferroelectric material is large, and a dipole moment has a tendency to align itself in a direction parallel to that of its neighbor. Assuming that the permanent dipoles are responsible for spontaneous polarization, we can write P equals to P0 into, which is equal to N alpha 0 EI is equal to N mu m LA. For higher temperature, A is equal to mu m EI by kBT, which is very small, and hence LA is equal to A by 3. Thus, P equals to P0, which is equal to N mu m square by 3 kBT is equal to EI. That is, P equals to P0, which is equals to N mu m square by 3 kBT into E plus beta P by epsilon 0. Or P equals to P0 is equal to N mu m square E by 3 kBT plus N mu m square beta P by 3 kB epsilon 0 T, or P into 1 minus N mu m square beta by 3 kB epsilon 0 T is equal to N mu m square E by 3 kBT, or P by E is equal to N mu m square by 3 kB divided by T minus N mu m square beta by 3 kB epsilon 0, which is equal to N mu m square by 3 kB divided by T minus theta c, where theta c is equal to N mu m square beta by 3 epsilon 0 Ke, and is known as ferroelectric Curie temperature. P by E is equal to C epsilon 0 by T minus theta c. where C epsilon 0 is equal to n into mu m square by 3 kb, which is equal to theta c by beta, and so C is equal to n mu m square by 3 kb epsilon 0, which is equal to theta c by beta. Now P by E into epsilon 0 is equal to epsilon r minus 1, which is equal to C by T minus theta c. This equation is known as Curie-Weiss law, and we have shown with the help of simple theory that a ferroelectric material obeys this equation at sufficiently large temperatures. The Curie point for Rochelle salt is above 24 degrees centigrade, and this substance has a very narrow temperature range of about 40 degrees centigrade within which it is ferroelectric. We shall now show that spontaneous polarization is possible in a ferroelectric material below the Curie temperature. We know that P is equal to Ps, which is equal to n into mu m into La. L is a function of A. For very low temperatures, A is very large, or for high electric fields, and hence La tends to 1. The polarization is called the saturation polarization Ps. When A is large, La is equal to 1 and n mu m is equal to Ps, is known as saturation polarization. Equation 6 becomes P is equal to Ps is equal to Ps into L of A, or P by Ps is equal to L into A. But La is equal to L into mu m Ei by kVt, which is equal to L into mu m by kVt into E plus beta P by epsilon 0. P by Ps is equal to L into mu m by kVt E plus beta P by epsilon 0. Spontaneous polarization exists if there is a non-vanishing solution for P in equation 7 with the applied field E is equal to 0. Hence, for spontaneous polarization, P by Ps is equal to L into mu m beta P by kb T epsilon 0. That is, P by Ps is equal to Lx, which is equal to cot hyperbolic x minus 1 by x, with x is equal to mu m beta P divided by kb T epsilon 0, and so P is equal to kb T epsilon 0 x by mu b. Now P by Ps is equal to P by mu m into n, which is equal to kb T epsilon 0 x divided by mu m square n beta. That is, P by Ps is equal to kb T epsilon 0 divided by mu m square n beta whole multiplied by chi is equal to T by 3 theta into chi. Thus, we obtain two simultaneous equations 8 and 10 which determine the condition of spontaneous polarization in ferroelectric crystals. Equation 8 gives the Langevin curve, which is, while the second one a straight line passing through the origin whose slope is T by 3 kb epsilon 0 divided by n mu m square n beta, which is equal to kb T epsilon 0 divided by mu mn square, and the slope increases with temperature. Langevin curve intersects with the first line at the point A. They intersect each other at the origin O at another point A, so that the solutions are P by Ps or An. But P by Ps cannot be a true solution because there is spontaneous polarization. Hence, the only possible solution is P by Ps or An, that is to say, a point of intersection of the two curves other than origin. As the temperature increases, the degree of spontaneous polarization decreases, and at very high temperature T greater than theta, there is no spontaneous polarization because the straight line does not intersect Lx curve. Measured values of beta of Rochelle salts are 2.1, BATY TiO3 is 0.44 and K is to PO4 is 0.37. The spontaneous polarization, which is the most characteristic property of a ferroelectric material, usually vanishes above a certain temperature Tc called the ferroelectric Curie temperature. In the ferroelectric region, that is below Tc, the dielectric constant is evidently a function of the field strength and is no longer a constant. One can of course define differential relative dielectric constant on the basis of equation 1, that dP by dE is equal to epsilon 0 into epsilon r minus 1. Generally, the derivative dP by dE is taken for the Virgin curve at the origin. The dielectric constant epsilon r, as defined by equation 11, may become extremely high as the temperature approaches the ferroelectric Curie temperature, as evident from figure, showing the variation of dielectric constant epsilon r as a function of temperature in BaTiO3 ceramics. The chain dotted curve pertains to a field of 1,10,000 volt per meter, while the solid curve refers to a field of 5,600 volt per meter. It may be seen that in the ferroelectric region, that is in the temperature range below Tc, the dielectric constant epsilon r is a function of field, epsilon r being higher for higher values of the field. However, for temperature exceeding the ferroelectric Curie temperature Tc, epsilon r does not vary with the field. For temperature exceeding the ferroelectric Curie temperature, the variation of absolute dielectric constant with temperature given by the Curie-Weiss law, epsilon is equal to C by T minus theta. So, the figure shows the dielectric constant of barium titanate ceramics as a function of temperature. Here we see variation of Langevin function with respect to x, and the second figure we see that how the epsilon r varies with temperature for BaTiO3 ceramic. Classification of ferroelectric materials. Ferroelectric materials may be classified into the following three groups depending on their chemical composition and structure. A. Tartarate group. B. Dihydrogen phosphates and arsenates alkali metals. C. Oxygen octahedron group. Table 2 indicates some of the materials which possess ferroelectric properties. For example, Rochelle salt, that is sodium potassium NaK C4H4O6 with 4 water molecule, and the Curie temperature upper is 23 and lower is -18. Spontaneous polarization is 0.25, which is highest for barium titanate. The Curie temperature is 120 degree centigrade and spontaneous polarization is 26 into 10 to the power -2 C coulomb per meter square. Tartrate group. A typical example of ferroelectric materials of this group is Rochelle salt, which is the sodium potassium salt or tartaric acid NaK C4H4O6 with 4H2O. This material was probably the first solid known to exhibit ferroelectric properties. This material has the unique property that it is ferroelectric only in the temperature range extending from -18 degree centigrade to 23 degree centigrade. Thus, the material has two transition regions instead of one. The figure shows the variation of spontaneous polarization PS of Rochelle salt with temperature. Other materials belonging to this group of ferroelectric materials are those in which a part of sodium in the Rochelle salt has been replaced by NH4, rubidium or titanium. Dihydrogen phosphates and arsenates of alkali metals. A typical example of this category is KH2PO4. The figure shows the spontaneous polarization versus temperature curve of this material. In this case, there is only one Curie temperature, namely 123 Kelvin. Oxygen octahedron group. Probably the best known ferroelectric material is barium titanate, that is BaTiO3. It is a representative of the so-called oxygen octahedron group of ferroelectric materials. Above the Curie temperature, that is 120 degree centigrade, BaTiO3 corresponds to the cubic structure presented in figure. In this structure, Ba2 plus ions occupy the corners of a cube. The centers of cube faces are occupied by oxygen ions. The oxygen ions form an octahedron at the center of which titanium ion Ti4 plus is located, the Ti of 4 plus is considerably smaller than the space which is available inside the oxygen octahedron. It thus brings with a high ionic polarizability for two reasons. One, it has a charge of 4 electron and it can be displaced over a relatively large distance. We shall see that this may be explanation for the occurrence of spontaneous polarization in BaTiO3. There is a intimate relationship between the ferroelectric properties and the atomic arrangement in ferroelectric materials. Above 120 degrees centigrade, BaTiO3 has the cubic structure as in figure. When the temperature is lowered through the critical temperature of 120 degrees centigrade, the material becomes spontaneously polarized and at the same time the structure changes. The direction of spontaneous polarization may lie along any of the cube edges, giving a total 6 possible directions for spontaneous polarization. Along the direction of spontaneous polarization of a given domain, the material expands, whereas perpendicular to the polarization direction, it contracts. Thus, the material is no longer cubic, but corresponds to a so-called tetragonal structure. BaTiO3 has two more transition temperatures, one at 5 degrees centigrade, where the spontaneous polarization changes its direction from one of the cube edges to a direction corresponding to a phase diagonal in figure, and one at minus 80 degrees centigrade, where the spontaneous polarization changes from a direction corresponding to a phase diagonal to one along a body diagonal. Associated with each of these ferroelectric transitions is a change in the crystal structure of the material. These three transition temperatures are reflected in the dielectric constant and in the spontaneous polarization of the material, as they may be seen in figure. The spontaneous polarization represented in figure was measured along a cube edge over the whole temperature range. Thus, the magnitude in the range between 193 Kelvin and 278 Kelvin is obtained by multiplying the value given in figure by root 2. PS in that region is directed along a phase diagonal. Similarly, to obtain the magnitude of PS in the region below 193 Kelvin, one should multiply the value in figure by root 3. PS directed along body diagonal in this case. In the figure, the cubic structure of BaTiO3 is shown above the ferroelectric Curie temperature, and the dielectric constant of BaTiO3 as a function of temperature is shown in the left panel, whereas the spontaneous polarization of BaTiO3 measured along a cube edge is shown on the right panel. So students, let us summarize what we have learned in this module. In this chapter, we had a detailed description of ferroelectricity and dipole theory of ferroelectricity, the different classification of ferroelectric materials in tartrate, dihydrogen phosphates, and arsenates of alkali metals and oxygen octahedron group. Thank you.